So hello everyone, welcome back to the another lecture. So my name is Ashish and today in the series of dual active bridge converter playlist, we are going to talk about the extended phase shift modulation in the DAB converter. Okay, so far so now we have learned about how the DAB converter operate, how the single phase shift modulation we can implement in the DAB converter, how to realize the closed loop control of the DAB converter, everything we have seen so far so now. Okay, and we have seen that how the soft switching happen in the DAB converter, and we have demonstrated in the Plex software as well, like turn on switching losses how is equal to the zero. That part we have already seen. Okay, now we will talk about the extended phase shift modulation in the DAB converter. So first thing we need to understand that why we are going for the extended phase shift modulation. Okay, so there are some problems in the single phase shift modulation, right? Because of those problems there is a need of some other modulations. Okay, so we will try to understand first the problems associated with the single phase shift modulation. What is the major problem associated with the single phase shift modulation? Okay, then we will touch upon the extended phase shift modulation and we will see the key waveforms associated with it. Okay, so this is very important that whatever problem we have, we will going to see in the single phase shift modulation, that can be eliminated with the help of extended phase shift modulation. Okay, and how the different waveforms will be look like in the extended phase shift modulation, those part we are going to discuss in this video. And in the next class we are going to see what are the important expression we are required in the extended phase shift modulation and how to get those expression, and then we will try to build up one script file. In the same way how we have built up the script file for the single phase shift modulation, we will try to build one script file for the extended phase shift modulation, like how we can compute the each and every parameter automatically and everything, and then we will try to run the simulation in open loop as well as in the closed loop. Okay, so in extended phase shift modulation also we are going to cover 3 to 4 lectures at least, and if required we will have another Plex simulation model also. There we will try to show you that how the exactly the problem is mitigated, the same problem we are going to discuss today. Okay, so this is all the things we are going to cover in this video and in extended phase shift modulation, and I hope so you will enjoy this. I have seen that there are very less video available on the extended phase shift modulation, or very less to zero video available where people have talked about the extended phase shift modulation. So I have gone through this topic really well, and I hope so whatever things I know about the extended phase shift modulation I can deliver to you. Okay, and thanks for your support, and thanks for commenting on the videos. So let's get started with this video. So here we are in our another screen. So now for the extended phase shift modulation in DAB converter, I am using one reference. Okay, I will give the link of that reference in the comment section or in the description of the video. You can use that reference, but I will going to discuss that paper in very detail with you. Okay, everything whatever we need to understand about the extended phase shift modulation. Okay, so this is the DAB converter image we have right now. It is different than whatever we have used previously. Okay, but structure is same. As you know that there is one bridge on the input side, there is another bridge on the output side, and basically how the power is transferred between the two bridges. So one high frequency AC will be generated at this terminal, and another high frequency AC is generated at this particular terminal, and whatever the phase shift is there between the input side bridge and output side bridge will govern the power transfer mechanism. Okay, and this can be represented by this simple diagram. Okay, so this part we already know how to compute the value of the L1 in the single phase shift modulation, how to compute the phase shift angle in the single phase shift modulation. That all part we have already discussed. Okay, now let us just recapitulate the single phase shift or traditional phase shift modulation. So what we have seen here and what are the problems associated with this single phase shift modulation, that part we are going to discuss. So now we have seen that what is the structure of the gate pulses we are going to give to these bridges. So S1 S4 will turn on at the same time, S2 S3 will be turn on at the same time in the complementary fashion, and S1 S2 whatever the nature of S1 and S2, they are just phase shifted by some angle or some time delay, and then Q1 Q4 will be turn on. So this is how we actually give the gate parts pattern. So this can, and what is this particular width we require, that part also we understood how to calculate, or we can realize this through control mechanism as well. Okay, we have seen the cascaded control, so using that also we can realize this. Okay, now what things we need to observe here. So we know that how it is operate. Okay, but what part we have not actually look upon, that we will going to see. So now you can see the waveform. So we know that VH1. So VH1 is the voltage that is going to be appear across this particular point. Okay, and VH2 will appear across this particular point. Okay, so let me just mark the some voltages here. So this is my basically VH1 will be coming here. Okay, and VH2 will be generated at this particular point. Okay, so these two voltages are there, and how these particular voltages will come and all, you know that. Okay, just apply the KVL, that part we have seen. So what things we have to observe here, VH1 and VH2 waveform we know, and VL is what, VH1 minus VH2 will give us the VL waveform. Okay, that part we know. Now what thing we need to observe is that basically you can see the nature of the VH1 and VH2. So VH1 has a nature of only two output, either it has some positive output or some negative output. Okay, that means either it is plus V1 or minus V1. So sir, this is generally we have already seen. So what is the thing we need to observe here? It has only two levels, that thing we need to understand. Okay, so VH1 has a two level, either plus V1 or minus V1. So what is the issue with this? Again, VH2 has a two level, plus NV2 or minus NV2. Okay, because of this VL has this kind of nature if we subtract them. That's perfectly fine. Now what is the nature of the IL? So IL also, how to calculate the waveform of IL, that we know. Now if I wanted to calculate what is my input power, how I am going to calculate the input power? So my V1, this particular voltage VH1 is there, and my current flowing through this is my IL. Okay, my current flowing through this is IL. So if I wanted to calculate the input power associated with this particular bridge, because this is, I am assuming that this is the input bridge, and what is the input power associated with this bridge is VH1 multiplied by the current flowing through this. Okay, so this is the two parameter is there. Now what is happened because of this, just see. So this is the nature of the power. Okay, if I multiplied the VH1 with the IL, this is the nature of the power I am going to get. Okay, now we have discussed one term that is called the backward power flow. You understood? I have just touched upon one term, and I told you that we will going to discuss the more thing about the backward power flow. So there is some sort of power which is there, which is going to be flow from output side to input side while during the operation of the converter. So this is the portion which is shown here. This is called the backward power flow, and you can see that this area is very large. Okay, so if I am operating my converter, and if this area is very large, then I am going to basically lose the some portion of my power during this transition. So this is the problem. This backward power flow in the single phase shift modulation is the problem, and this will create a really big problem when you go. Our motto is not like we need to do the simulation. Okay sir, we have provided some input, I am getting my output, so that's the end of the story. No, this is not we wanted to find out the best possible solution to realize the hardware. Okay, doing the simulation, getting the result, this is not the ultimate aim, right? We need to know what exactly is happening. Okay, so this is the portion where my power is going to be back, and this is the loss in the system. Now with this I have written down few things here, and we will just try to understand those points. So I have written down some points here, like problem with the single phase shift. So I have already discussed that this backward power flow is the problem. How exactly this is the problem, I will tell you. Okay, so control of the power flow is depend on the transformer leakage inductance that result into the great circulating power and current stress when the value of the V1 by n times of the V2 deviated from the 1. So that part we have seen in the basically soft switching curve. So we have seen that V1 by n V2 that factor is there, and if this value m, we called it as a m value. Okay, so m factor. So if the m factor is deviating from the 1, then that time it will go into the non-ZVS region, and because of this losses in the system will be more. So those are some different losses. Okay, in addition to that there is another losses. This losses is called as the backward power flow, and then the loss in the power divisor and magnetic component increase and the efficiency of the converter reduces. Okay, so that we know. what people have done, so basically people know that okay, so has some particular range, so ZVS has some particular range. So if we need to overcome this particular problem, what people have done, okay, so people have started to find out the some solution. People have not directly jumped to the extended phase shift modulation. Okay, so this is the thing which we are going to discuss in this video, but people have not directly jumped. So people have observed that okay, so there is a problem with the soft switching. Okay, if the value of the M deviates basically from 1, then there is a problem, so soft switching will not happen. So what people have done, in some of the studies, the duty ratio of the driving signal of each of the semiconductor devices is varied and should be calculated online, that increase the complexity of the system. So what people have tried to do, so we have seen that in single phase shift modulation we have used the fixed duty ratio, like 50% duty ratio, okay, for all the switches. So people have tried to implement that. This thought should come in your mind as well, because I am hoping that most of the viewers who are watching my videos, though they are basically doing some research kind of stuff. So it's your job to basically you have the MATLAB, just try to do the different combination, like let us have the S1 30%, S4 70%, this kind of combination you can try, and just try to run the simulation. What result you are going to observe, those are the points which will lead to some problem statements. Okay, because this is how we do the research. Okay, it is not like we know the things, we will try to do the things, and if we are getting the output, that's the end of the story. No, this is not the way we are going to do. Okay, we need to find out something additional. Okay, we are learning this part just to understand the concept, but out of this concept we need to find out some other alternative, right? So this is the first alternative people have tried. So people have tried to use some different duty ratio, and they have observed something, but this is some sort of complex thing. So if you wanted to refer the references for this particular work, you can use these two references. Okay, so I have just listed down these two references. You can just search this paper, you will get the information about this particular work. Okay, how the duty cycle is varied, and they have tried to come up with some sort of solution to have the increase the ZVS range. Some studies are focused on how to extend the soft switching range of the or eliminate the reactive power. Basically, we have told you that some people call this backward power flow as a reactive power, but this is part of the reactive power. Okay, it is not a complete reactive power. That part we have already told you. And how they have tried to extend the soft switching zone in the single phase shift modulation, for that you can refer this particular paper. I have not gone through in detail of this paper. I have just seen what is their approach, basic fundamental thing you should try to see in the paper. Okay, just open the papers and try to observe what things they have done. Okay, so these are the two approaches they have basically tried to do. Now how the third approach come, that part we need to understand. We are talking about the extended phase shift modulation, but what is extended phase shift modulation? Why, how this particular concept come? So we know that okay, so backward power flow, this is the area where the backward power flow is happening, right? So how, when this particular thing is happening, so at this time when my current is negative, from my current from some negative value, it is going to the positive value. So this is the area where my backward power flow is happening. So IL is there, which is the primary side current. Now for calculation of the P in, what I need, IL as well as VH1. Okay, now what is the value of the VH1 at this particular time? So you can see that VH1 is nothing but basically some positive value. So this positive value multiplied by this negative value will have some negative power, and that power is going to the my backward power flow. Okay, now what solution we have? Either to make, just like the soft switching concept, either to make the IL equal to 0 or to make the VH1 is equal to 0 at this particular duration. So people come up with some sort of modulation. That modulation we call as extended phase shift modulation, where they have tried to make this voltage as a 0. So initially it is negative, and then people have tried to make this voltage VH1 as a 0. And how to do that? That has done with the help of extended phase shift modulation. So how we are going to give our gate patterns to the signals that will determine what is the voltage at this particular duration. And if any of the parameter, either IL or my VH1 is equal to 0, then that time this backward power flow is going to be 0, because the product of these two only determines what is my P in. Okay, and that is the power which is going back. So if I am able to make this VH1 is equal to 0 from this duration T0 to T0 dash, then I am able to make the backward power flow equal to 0. So this is the very fundamental concept. So basically this is what it is written here. So VH1 should not be conformed to the square waveform. So it is a square waveform. So that is why I am saying initially that it has only the 2 level. So if it is possible to make it as a 3 level, so plus V1 minus V1, and in addition to that we added another level, that is a 0 level. So if that 0 level is came into the picture, then this backward power flow concept will be 0, and this is what we want. Okay, so another thing is written down here just about the backward power flow, the same thing whichever I have discussed so far. So now the same thing are mentioned here. Okay, so you can just read it out this point. This is just for your reference. I have added so that if you are taking the screenshot or something, you can have everything with you. Okay, so try to make the notes. That is the best thing you can do. Now one of the interesting thing I wanted to tell you. Okay, so just focus on that. These are some interesting point you should understand. So if you have basically some AC source, okay, which is connected to the your active front end converter. So on active front end converter, we are going to start the one new playlist. Okay, so please watch that playlist. That is also going to be a comprehensive playlist. So active front end converter we have. So what is active front end converter? This is a power factor correction circuit. Okay, which will convert the AC to DC. At the same time it will improve your power factor. So now let me tell you that if I have my some sort of AC to DC converter, that is active front end converter, for some particular power load P. Okay, if it is carrying, if this basically supply is carrying the peak current of, suppose let us say for 30 ampere peak, the supply current for the system is 30 ampere peak input current. Okay, peak current I am talking about, and my power requirement is like, suppose P is equal to 10 kilowatt. Okay, so 10 kilowatt I have my power requirement. Okay, and here is one resistive load. So I have resistive load and this AC to DC converter, and my power requirement is 10 kilowatt. So it is drawing the 30 ampere of the current. Now what is happen when when I replace this load with my DAB converter? So let us say I wanted one isolation state. So I have added one DAB converter here. Okay, so DAB converter I have added here. So if I add the DAB converter and then if I will use my basically load, and I have the same I have my same output requirement of the 10 kilowatt, only one more converter stage I have added. So what is the effect happen on my input current? So one of the viewer I have asked him, he has simulated this active front end converter with the DAB. So if you simulate the active front end converter for 10 kilowatt suppose, and you have the resistive load, that time your input current peak current requirement is 30 ampere. But when you connect the DAB converter in place of this DC load, and you are connected this basically resistive load at the DAB converter output and having the same power requirement, that time your peak current value is changed. So ideally it should not change because my system is same. Okay, I am only adding one basically power electronic stage. So maybe because of some losses, this current from 30 ampere should go to 35 amperes, right? That is only the very nominal change we might expect. But what is happen exactly is, because of this backward power flow, this current goes from 30 ampere to nearly 50 ampere or 60 ampere. So this is a really huge thing. Okay, and now my converter demand the very high input current, and which is not the good thing, right? If you are using some one phase system, then it has some basically fixed kind of current requirement, right? So, and this current is not good. Initially we have done our work in 30 ampere, now I need the 50 ampere, right? So why I am telling all these things is that when you are, because it is not like when you do the DC to DC DAP converter simulation, you are not seeing the current waveform. You are seeing the current waveform, but you are not actually observing the effect of input current. So when you have when you are going to simulate the DAP converter, so you have the DC fixed input voltage, you might observe the input current peak, but that time it is not that visible to understand. But when you do some cascaded type of the things, that time this effect is really visible. Even though I have seen that, even I have done this simulation, so there also I have observed that basically the current is really high. So 30 ampere to 50 ampere, some sort of change is there. And one more important thing I wanted to tell, I forgot, I guess, that I wanted to mention, okay, so even though my power factor is unity, my input current, input voltage, both are almost sinusoidal, where THD is less than 5%, still I have observed this phenomena. So that means that when I am going to use the single phase shift modulation of the DAB converter, there is a really big power flow issue is there, backward power flow issue is there, and this issue we need to mitigate. So for that we are going to use some another approach which is called as extended phase shift modulation. That part we are going to see just after that. But if you have to do some research, you can think that in single phase shift modulation only, how we can basically try to eliminate this backward power flow. Is it possible or not? How we can do? So these are the open-ended research question. Okay, so if you wanted to work on this part, this is really a great thing. Okay, so you can work in this direction as well. Okay, but apart from this, let us come to our important part of this lecture, which is nothing but the extended phase shift modulation. So far so now we have learned that, okay, why there is a need of some other modulation technique apart from the single phase shift modulation technique, right? Because in single phase shift modulation technique there is a problem of the backward power flow, and this is a really big problem. Okay, and this is the open-ended research question as well. Now we will start to understand the extended phase shift modulation. So in one of the video we have seen that basically what is the extended phase shift modulation. So we have seen that basically we are going to phase shift the duty cycles, like in single phase shift modulation, S1 and S4 are turned on at the same time, and S3 and S4 are turned on at the same time. Now what we are going to do, we are not going to turn on S1 and S4 at the same time. This condition is there that S1 and S2 are not going to turn on at the same time, because if they are going to be turned on at the same time, this is a shorted, so my supply is shorted. So this condition should be there. But what I am changing is now I am not going to turn on S1 and S4 at the same time and S3 and S2 at the same time, but I will keep the Q1 and Q4 turn on at the same time and Q2 and Q3 turn on at the same time. So this thing I am going to keep. That is why it is called as extended phase shift. In double phase shift we are going to change the Q1 Q4 timing turn on. We are not going to have the Q1 Q4 turn on at the same time, but that is the concept in the extended phase shift. Okay, but now we are talking about the that is the concept in the double phase shift. Okay, but here we are talking about the extended phase shift. So what I am saying that S1 and S4 I am not going to turn on at the same time. So how the sequence is, so let us say I have turned on, just observe the waveform. So I have turned on the S4 here, and after some time I have turning on the S1. So S4 is turned on, and then after some time I have turning on the S1. So then for a particular duration S1 and S4 both are turned on, and then S4 is going to be turned off, but still for some particular again duration S1 is turned on, and then it is 0. And when S1 is turned off, I need to turn on the S2. Okay, and S1 and S2 are complementary to each other. Similarly, S2 and S3 are having the same kind of thing. So S3 is turned on initially, and then after some time with the D1 THS delay, basically S2 is going to be turned on. So what is happening because of this, that we need to understand. So just a few convention which I have used here. D1 is the phase shift ratio between the driving signal of S1 and S4 or S2 or S3. So basically this is the phase shifting I am going to provide in between the my one bridge also. And D2 is just like our phase shifting angle phi or delta, which we have used in the previous classes. So D2 is the phase shift between the primary and secondary voltage of the transformer isolation. So basically whatever phase shift we are going to give between the two bridges, that is my D2. Okay, and basically whatever the phase shift I am going to give between this inner bridge, that is S1 and S4 or S3 and S2, that is my D1. Okay, so there are now two phase shift we are going to observe here. Okay, so two phase shifts are there. So how to compute the D2, that part we have already seen. Okay, and we will try to understand in the next lecture as well how to compute the D2. But another thing, how to compute the D1, that part also we are going to discuss in the next lecture. But what is important thing we need to understand here is that what will happen because of this. So now S1 S4 I am going to turn on at the different times. So what is exactly happening? What is the problem we are trying to solve? Backward power flow. So whether with this kind of the switching pattern, whether I am going to eliminate the backward power flow or not, that part we need to understand. So let us try to observe the waveform. So what is happen, just initially see here first. Okay, just try to concentrate here initially. So what I told you that if I am able to make the voltage of the VH1, so this is the voltage of VH1. So if I am able to make the voltage of VH1 equal to 0 between that particular duration, then basically voltage and current multiplication resulted into the power, input power, that part I can make a 0. Now when S1 and S4 are turned on, what is my this VH1? It is nothing but the V1, right? What if I will say S4 and S4 and S2 are turned on? So here you can see that S4 and S2 are turned on at one particular point. So if S4 and S2 are turned on, then my current will flow here only, and that time what is the voltage here? That is going to be 0. Why 0? Because input is not connected right now. So if S4 and S2 are turned on at the same time, then current will circulate here. If S1 and S3 are turned on at the same time, the current will circulate here only. Okay, so one through the switch, another's body diode. So this is how we are trying to make the output, we are trying to make the voltage across this particular branch as 0. So we are turning. So initially we have seen that these two switches are never going to be turned on at the same time, right? And these two switches. But now because of the phase shift we have provided between these two particular, this cross diagonal basically bridges, cross diagonal switches, this can be happen. How? Just let us try to observe through the waveform. So let us see the waveform, and basically for your convenience, basically I have all the images of what will happen in which mode. Okay, so just try to observe what is the basic concept behind this. I have just told you. Now you can see this particular duration. So let us see this. So what is happen here? So my S2 and S3 is turned on. So when S2 and S3 is turned on, what is my output voltage? Here it is coming as minus of VV. So let us see in the figure. S2 and S3 are turned on. So S2 and S3, if these are turned on, so we know that this operation, fundamental operation, we know when S2 and S3 are turned on, that time my output voltage is equal to this VH1 is equal to minus of V1. Okay, the same thing we are observing here as well. Now another instant is what? My S2 is basically on and my S4 is on. So when S2 and S4 is on, so let us say S2 and S4 is on, that time I told you that the current will circulate here only, and VH1 will see the voltage of 0. So that is why you can observe that the voltage here is 0. Okay, so VH1 has now 3 voltage level. One is minus of VH, another is a plus of VH, and we have introduced another level, that is a 0 level. And this is the way we have implemented it, and because of this what will happen? So this is the duration and this is the nature of the current. So you know that rest of the thing we have already learned. Okay, so I am not emphasizing on that. So if you are new to this channel, directly watching the extended phase shift modulation, just please go back and watch the entire series. It's a really great series. This is what I feel, and you will not find this video anywhere. And I'm trying to explain the things in really from basics. Okay, so how we have make the VH1 0, you understand. Then VH2, just apply the basically volt second balance, just a simple KVL expression, so you can easily find out the VH1 VH2. That is the part you already know. And then VL is what? VH1 minus VH2. Then you can just draw this waveform as well. Now here just I am making one assumption that VH1 is greater than VH2. Okay, and because of this, when I do the VH1 minus VH2, I have some again a small amount of the negative voltage of the VL. Okay, that is because I am assuming here is that VH1 is greater than VH2. Okay, so this is the how we can get the nature of the waveform. Now what is the nature of the current? So that is also we have understood that just by observing the nature of the VL, we can draw the nature of the IL. Okay, and this is how we are going to get the nature of the IL as well. Okay, so these things we have learned in detail in the single phase shift modulation. That's why I am not going to explain the things of how the VL waveform come, how the IL waveform come. Okay, so these are very fundamental thing. We have explained this all the things. Okay, where I am interested here is that how we are making the backward power flow 0. So now I have VH1 equal to 0, I have some current, so its product again going to be a 0, and this is how we have eliminated the basically backward power flow. So basically during this small instant of VH1 on, or this current is there, very small amount of backward power flow is going to be happen, and this is very small amount. Okay, so this will not cause that much damage to our system. Okay, as compared to what we have saw, this is the entire figure we have seen in the single phase shift modulation, but in a extended phase shift modulation, very small amount of the backward power field flow. Okay, so these are the different modes basically we can have for this particular figure. This is very self-explanatory. Okay, what is the main concept we need to understand from this video? Like how we are going to realizes the extended phase shift modulation, and what is the limitation of the single phase shift modulation. That part we have seen, and these figures are there. You can just see the figures and have these modes with you and this image with you. Okay, if you are basically taking the screenshot for a better understanding in the future. Okay, so all these things we have understand. So what we are going to do, we'll stop here, and in the next class basically we will try to understand. So with this basically waveform, how to calculate the expression of power, that part I am going to skip. Okay, because how we have seen in the single phase shift modulation that this is a lengthy procedure to have the charge balance and everything, and we need to go through a lot of derivation, then we are coming with the some power expression, right? You have understood, and that is there. Okay, now what we will going to do in the next class, we'll have the expression, we will write some basic fundamental expression from this particular waveform. Okay, and then we have the expression for the my output power, maximum output power, and then we will try to compare them with the single phase shift modulation, and then from this we will try to get the value of the d1 and d2. Now I told you that okay, this is my d1t, d2 is my d2. Okay, but what is the value? So we have learned in the single phase shift modulation how to calculate the d2, whether the same d2 is available in the extended phase shift or not. That part we need to see. How to compute the value of the d1, like in between the similar bridge, what is the phase shift we need to provide, in between the input and output bridge, what is the phase shift we need to provide. So those two parts are very critical, that we are going to learn in the next class. Okay, so if you understand those parts, then it is very easy to implement the open loop simulation. Okay, and then we will see that okay, how exactly the power is transferring, that part we already know, and we will simulate this particular thing, and we will try to understand okay, this is how we realize the extended phase shift modulation, and we will try to observe the result. And then once that is done, we will come up with maybe a closed loop simulation, where how exactly automatically this d1 and d2 are calculated through some control. That part we are going to see, and if require, again we will go through the some sort of the plex simulations. Okay, and then once that is done, then we will move forward for the some next task. Okay, like we will try to understand the double phase shift modulation. So this is what I am planning so far, but sorry, really sorry, because of the time constraint, I'm not getting too much of time to make a videos, and sorry for that. Okay, but once I get the time, I will definitely make the video, because I have the content, but because of my schedule, sometimes it's really difficult to find the time and make a video and upload it. Okay, but anyway, I'll try to make a video and upload it, because I also wanted to make this playlist comprehensive, and most of you are maybe working on the DAB converter, so that will be really helpful for everyone. Okay, in future also, please share with your friends who are working in the DAB converter and all. Okay, so that maximum people can watch these videos and all. Okay, if you are thinking that these videos are okay and good, you can like, comment and share, okay, with your peoples. So with this, I'll conclude this lecture. Thanks for watching this video. We'll see you in the next class.